Good afternoon. My name is Mike Johnson. I'm Chief Executive of the Dairy Council for Northern Ireland, and we're delighted to be hosting today's EU Sustainable Dairy Symposium. Thank you for taking the time to join us this afternoon. It's very much appreciated, and I hope you find the various presentations and videos of interest. I'd also like to extend a very warm welcome to dairy industry colleagues from across Europe and indeed further afield. So wherever you're watching from, you're most welcome. Our Sustainable Dairy Programme is being run in partnership with the European Milk Forum and with very welcome financial support from the European Union. Today's event is part of a 3-year programme to support and promote sustainable dairy practices across Europe and in Northern Ireland in particular. And as well as today's symposium, the programme will include a 2020 Northern Ireland fact book and a couple of virtual farm visits. These will be happening over the next couple of months, so please keep an eye out for information about them. Now, a few housekeeping rules before we get started. Since we won't be taking any questions after each presentation, please submit them to the host through the chat function, and we'll be able to put some of them to the panel later. The event is being recorded and the link will be emailed to you, as well as being posted on the Dairy Council website. And lastly, we would encourage you to engage with the event online through Twitter and Instagram. We would just ask that you tag the Dairy Council in your posts and use the hashtag SustainableDairyEU. Now, the purpose of today's event is to showcase the significant strides that have been made in reducing emissions on dairy farms throughout Northern Ireland. Even though what has been achieved is commendable, we do recognise that there is no finish line when it comes to sustainability and climate action. We cannot relax our efforts to reduce our emissions still further. But if we're to succeed in this, then we need robust research to identify ways in which dairy farming can adapt to improve efficiency, as well as continue to grow in ways that are not harmful to our environment. So the purpose of this afternoon's symposium is to show how this has been happening, how research that has been undertaken by AFBI and CAFRE is being adopted and applied on dairy farms in Northern Ireland, with beneficial effects on emissions. In this afternoon's symposium, we'll have contributions from 2 keynote speakers: the Minister for Agriculture, Environment and Rural Affairs, Edwin Poots, MLA, and Professor Frank Mitloehner from UC Davis. We'll also be hearing about sustainable dairy projects being carried out by AFBI and CAFRE, and I'm delighted to welcome back Dr. Stefan Peters from the Dutch Dairy Association for an update on the nutritional role of dairy in sustainable diets. We're also going to hear from 3 dairy farmers about the systems and processes they have put in place to improve our local environment, all of which are based on research projects carried out by AFBI and CAFRE. But first, we're delighted to have Minister Poots join us today. A farmer himself, he has a firm grasp on the environmental issues facing farm businesses across Northern Ireland. And can I take this opportunity, Minister, to thank you and your colleagues for the support that you've given the sector during these difficult times. Minister Poots.
Ladies and gentlemen, I would like to thank the Northern Ireland Dairy Council for the opportunity to speak at today's Sustainable Dairy Symposium. I commend you on the measures taken by the Northern Ireland dairy industry to improve its sustainability. This afternoon, I'd like to briefly outline the new green growth strategy and delivery framework and the key environmental challenges faced by government and industry. I am sure that we can all agree that the core objective of the dairy industry here is to produce high quality food. If the Northern Ireland dairy industry is to remain viable, then it must outperform its competitors from a productivity perspective. However, these gains must be achieved in balance with environmental sustainability. In today's world, farmers need to farm in a way that is environmentally sustainable. Around 70% of land in Northern Ireland is devoted to agriculture, so whether it be air quality, water quality, biodiversity, general land or soil management, agriculture has a very significant impact on the environment, and this can be both positive and negative. Our economy is changing. Over the next 30 years, it will become largely unrecognisable. There are many reasons for this, but perhaps the single most important of these is the commitment by the UK government to achieve net carbon zero by 2050. Overall, we have reduced our emissions in Northern Ireland by 18% in recent years. We've gone down from emitting 24 megatons of carbon dioxide equivalent in 1990 to 20 megatons in 2017. While this is not enough, it proves that we can make progress when we work together. In terms of the challenges that face us, I will start with the challenge to improve our air quality. In common with any region or country with large livestock numbers in their supply base, Northern Ireland is a significant contributor to local greenhouse gases. While UK agriculture only represents a 10% contribution to the GHGs nationally, locally we contribute around 27%. I commend the tremendous efforts made to date by the dairy sector in partnership with DAERA through the Efficient Farming Cuts greenhouse gas strategy. The 34% reduction of carbon intensity per litre of milk since 1990 is a significant outcome indicator and a big step in the right direction. I think this initiative also clearly demonstrates the importance of industry and government working collaboratively. As you're aware, further work is required, in particular in research programmes, to identify how we improve the balance of agri-emissions and storage of carbon via healthy soils and woodland, but it is important to recognise the progress to date. Ammonia emissions are a significant challenge for the industry in my department, as well as a threat to the sustainability of the sector. But it is a challenge which is surmountable. We need to reduce ammonia emissions by implementing technologies and other measures on farms. Farmers have already begun this transformation through their uptake of technologies such as low-emission slurry spreading. And we'll continue this change. We need to support, and I hope that we can have that from both government and the wider supply chain. My department has developed a series of proposals for ammonia reduction, and we'll be consulting on these soon. Many of you will be aware of the recent communication on the scientific evidence around ammonia, and particularly the importance of grazing systems in the dairy sector. I want to work with industry to identify the best way of minimising ammonia emissions while supporting a thriving dairy industry, and look forward to hearing your views during the consultation. It is widely recognised that soil health is a key component of environmental sustainability. One of the expert working group's recommendations to DAERA on sustainable land management was to carry out province-wide soil sampling and analysis of our farmed lands. My department has supported the delivery of 4 extensive soil sampling pilot schemes across 3 water catchments and a Northern Ireland-wide component. Collectively, these pilots constituted a publicly funded intervention where 1,613 farms with fields spanning 49,711 hectares had soil samples collected and analysed. My department will continue to support measures that improve sustainability in the Northern Ireland agri-environmental sectors, including progressing a strategic outline case for a soil nutrient health scheme. Biodiversity is also important. This is an area of major concern with many of our farmland species and habitats under pressure and in decline. A key measure to arrest these trends are agri-environmental schemes. After 3 annual intake tranches, some 4,900 farmers are participating in the environmentally farming scheme. Historically, the dairy sector has not seen significant applications to agri-environment schemes. Some dairy farmers perhaps think the EFS is only for those who farm more extensively. However, many of the main pressures on biodiversity and water quality that the scheme aims to address are often greatest in areas where there are many dairy farmers. A further environmental priority is improving water quality. Good progress has been made since 2007, and the dairy sector has made a really significant contribution to this achievement. However, major challenges remain, particularly the issue of excess phosphorus and its negative impact on the water quality in our rivers and lakes. The most recent water quality data indicates that since 2015, the long-term downward trend in phosphorus levels in fresh waters has stopped. In some areas, phosphorus levels are now increasing due to inputs from agriculture. This is also a major concern, as around 39% of our water bodies in Northern Ireland do not meet targets for good water quality due to elevated phosphorus levels. The cumulative phosphorus surplus over many years in Northern Ireland agriculture has caused phosphorus buildup in many soils. A recent survey indicates that some 50% of soils on dairy farms are above their agronomic optimum phosphorus status and therefore at risk of phosphorus runoff to water bodies. So in addition, an increasing reliance on concentrate feeds is contributing to a rise in Northern Ireland's agricultural phosphorus surplus. Getting the fundamentals right at the farm level is key. Soil analysis, nutrient management planning, reducing phosphorus inputs and best practice in the efficient management of manures and fertilizers. So we need to really focus on reducing phosphorus coming onto the farm in fertilizer and feed and using nutrients more efficiently to help improve water quality. We also need to increase the use of low emission slurry spreading equipment such as trailing shoe systems. These deliver a range of productivity and environmental benefits, including increased nutrient efficiency, reduced need for chemical fertilizers, and lower ammonia emissions. It's also an example of efficient farm delivering improved environmental performance, and that's a win-win situation. It is DAERA's desire to support the industry to meet the environmental challenges I've outlined, and one major step in the direction was the formation the Knowledge Advisory Service based at CAFRE. The Knowledge Advisory Service brings together existing advisory functions provided by CAFRE along with agri-environmental advisory functions formerly provided by the Department's Countryside Management Unit. The primary role of the Knowledge Advisory Service is the holistic development of farm and food business where economic and environmental performances are inextricably linked. From an environmental perspective, the Knowledge Advisory Service enables DAERA to better integrate environmental advice into its support to the agri-food sector. The Knowledge Advisory Service will drive farm and food business practices and behaviours that will lead to improved productivity and profitability, as well as enhanced environmental performance and resilience. So while it must be accepted that agriculture can exert negative environmental impacts, it also has the potential to deliver major environmental gains. And this must be of particular focus in any new agriculture policy framework. DAERA is leading in the development of a multi-decade green growth strategy and delivery framework for Northern Ireland in partnership with other departments, local government and stakeholders from across the business and voluntary sectors. The outcome will be a framework of programmes which will help deliver a resilient recovery through a greener, low carbon and circular economy for Northern Ireland. The foundation programmes will align with the major sources of carbon emissions and in addition to agri-food are expected to include innovation in energy, sustainable transport, business, residential and waste. It is not generally economically viable for individuals or companies to take individual action to improve the environment if this is not rewarded or incentivised by the market. Therefore, there is a strong need to use an appropriate balance of regulation, incentives, education, knowledge and technology transfer to effect this change. To ensure that any future Northern Ireland agriculture policy is developed in a way that the combined actions of the local farming industry are environmentally sustainable, then the following principles should be borne in mind. Any future policy framework should fully recognise the environmental impacts of farming. That is, current farming and land management practices should not compromise our environment for future generations, but should seek to deliver a positive environmental legacy. That future environmental payments or incentives should recognise and reward public goods provided by farmers and land managers. Farmers and land managers will have to change and adapt to meet the future environmental challenges and thereby ensure the long-term environmental and economic sustainability of the agriculture sector. So in order to achieve this change, farmers need to be given the correct information and knowledge at the right time on why they are being asked to change, how to achieve this change, and what benefits are for them and for the environment. Regarding regulation, I am sure that you will appreciate that any agriculture policy framework will need to be underpinned by appropriate and proportionate environmental regulation. Environmental regulation should form a backstop to ensure that farming practice does not cause unacceptable pollution or damage to habitats. To help farmers and land managers adapt and change to meet existing and future environmental challenges, there's also a need for increased emphasis on behavioural science, education, knowledge transfer and professional development. It is vitally important that we need to ensure that in future farmers and land managers have access to relevant, timely and up-to-date information, knowledge and technology transfer on how to deliver environmental sustainability and enhancement of their land throughout their careers. Northern Ireland's farmers need to make the best use of the research available to deliver that best practice in relation to environmental and conservation management in the agriculture sector. There is a need for continued investment in research to underpin sustainable agricultural policy development and to facilitate practical environmental management, knowledge transfer to farmers and land managers. So schemes to incentivise changes in farming practice to enhance environmental sustainability could have a significant role to play in future agricultural policy. In working to achieve this environmental outcomes we may need to look at new ways of working and engaging with the industry. Indeed, policy instruments may need to facilitate greater involvement of others such as farmers, food processors, local authorities or non-governmental organisations. So in conclusion, I am quite clear that achieving tangible and enduring improvements in sustainability across all of the environmental issues impacting on Northern Ireland's dairy industry can only be achieved through a wide range of approaches, and government cannot address these issues alone. I and my department officials want to work with stakeholders such as yourselves for insight and to identify solutions which we can jointly implement. Only a truly collaborative approach can deliver the future sustainability of Northern Ireland's entire agri-food sector. Achieving that position will not be easy. However, we all have an obligation to build on progress so far through embracing the many challenges and seizing all opportunities to further improve the sustainability of Northern Ireland's dairy industry. Thank you.
Thank you, Minister, and it's encouraging to hear that the work of the sector has been recognised within your department, and certainly we look forward to working with you and your colleagues in the future to reduce emissions even further. Given the time difference between Northern Ireland and California, I'd like to thank our next keynote speaker, Professor Frank Mitloehner, for taking the time to record his presentation and to make himself available for the panel session later. Professor Mitloehner.
My name is Frank Mitloehner, and I'm a professor and air quality specialist in the Department of Animal Science here at UC Davis. And thanks for having me and talk to you about the path to climate neutrality, a path that I think livestock is about to go on. I want to break the ice with you by talking about a trip I recently did to Ireland. I left California and I flew over Los Angeles, and you see an image here. And what you see when you look out of the window is pretty frustrating. I mean, all you see is people, houses, streets, harbors, airports, and so on. Los Angeles is a city with 13 million people. 13 million people. One of the largest in the country, in the US. And I always found it amazing how you make life like this happen. But, you know, very little green, very little green. So I flew over LA and looked out of the window, took this photo, and then kept going, flew over Europe. One of the other sites I saw was a major power plant in Poland, a coal-fired power plant to be precise. It's the largest coal-fired power plant in Europe, and I thought about emissions, needless to say. That's what I do, I'm an emissions specialist. And then, last not least, I flew over Ireland. And what did I see there? Well, I saw a lot of green. And then I thought about how to break the ice with Irish audiences. And so I decided to look into the carbon footprint of these respective sites. Los Angeles with 13 million people, this power plant, major power plant, and then the country of Ireland with 4 million people total population. And I was very surprised because when I looked at the official emission inventories for these three sites, I found something that most people wouldn't expect. Most people looking at that would say, clearly LA must have the greatest emissions. And maybe number 2 should be this power plant, and maybe number 3 Ireland. That's what most people tell me who I ask. But that's not true. What you find when you look into the emission inventories is that LA has a carbon footprint of 50 million metric tons of greenhouse gases. So it's called carbon dioxide equivalent, CO2e. This power plant in Poland has a carbon footprint of 40 million metric tons, and Ireland a carbon footprint of 60 million metric tons. So the winner here is Ireland. And when I looked at that, I thought, how in the world is that possible? Ireland has 3 to 4 times fewer people, and it really is as green as it looks when you look at it from space, from a satellite, or from a plane. So how is that possible? And I believe one of the reasons is the way we quantify one of the main gases from Irish agriculture, which is methane, which is a major challenge, because I think that it is not quantified in an accurate way these days. And I will talk about that more in a few minutes. The other issue I have with this is that what you see there as being green is a bunch of biomass, grasses, legumes, bushes, and trees, all of which have one thing in common, and that is that during photosynthesis, they pull in a lot of carbon, and that carbon then goes into the soil, where it's sequestered, meaning stored for a long time. Most of this land that you see when you look at Ireland, most of that land is marginal land and used for grazing. In other words, a lot of the carbon that's pulled out of the air is pulled into the ground, and because it's not tilled, it stays there for a long time. This process, by the name of sequestration, is not really accounted for, but it is a very important sink of greenhouse gases. So all of these things, of course, don't matter for LA or for this coal-fired power plant, but they really do matter for Ireland. So in my opinion, it is particularly important for your country that we get it right, that we get the contribution that particularly livestock has to climate right. And that's what I'm here to do for you today. This slide is an important one. It shows how currently greenhouse gases are compared to one another. It is referred to as the global warming potential, or GWP 100. GWP compares the different greenhouse gases based on how they compare to CO2. So this overall matrix was really developed back in 1990, so 30 years ago now, to help policymakers compare greenhouse gases and their relative strength to one another. And the scientists at the time came up with this unit, and they had a bunch of footnotes underneath a table. The table looked much like what I'm showing on this graph, but a bunch of footnotes underneath. The footnotes were warnings telling the viewer, telling the reader to be careful, because it's not just that these gases differ with respect to how much they warm up when the sun hits them, but that there are other differences as well. So, in general, methane is much more potent in trapping heat from the sun than CO2 is. To be precise, 28 times more potent, and that's expressed as the global warming potential of methane. Nitrous oxide even more so, 265 times the potency of CO2. So what these people back in 1990 did was they came up with the relative difference in potency of these various gases. And it acknowledges the difference in source strength, meaning in the ability of these gases to trap heat. But that is only part of the picture, which is now becoming more and more clear and more important to people in animal agriculture, which I explain in a second. This slide here is an important one. It shows the so-called global methane budget. Global methane budget. On the left side of the slide, you see various sources of greenhouse gases, in this case of methane. You see fossil fuel production, agriculture and waste, and other sources, all of them amounting to a total of, and that's the first half bubble to the left, 560 teragrams of methane per year. 560. What most people who discuss methane don't discuss, for reasons unknown to me, is that methane is not just produced, meaning they're not just sources of methane, but as you can see on the right side, there are sinks of methane. Sinks always means there are activities that pull methane out of the atmosphere. And as you can see, these are not trivial. The total sinks in the world amount to 550 teragrams. So again, sources are 560, sinks are 550. So the net methane in the world is not 560, and that's what you hear and read a lot, but it's 10. Because, again, methane is not just produced, methane is also destroyed. Methane is what we call a flow gas. A flow gas, which is a very different type of gas compared to CO2, to which it most often is compared. So when you look at the sinks here on this slide, you see this large arrow pointing downward. And it says sink from chemical reaction in the atmosphere. This chemical reaction that they are referring to is called hydroxyl oxidation. What that means is that the methane molecule that's in the air sooner or later finds another molecule that's called a radical. And this radical steals hydrogen away from the methane and converts it into CO2. Again, hydroxyl oxidation is the name, and it takes about 1 decade for that to happen. This slide here shows the lifespan of these various greenhouse gases, namely one of 1,000 years in the case of CO2, over 100 years in the case of nitrous oxide, both of which are long-lived climate pollutants. So once these gases are in the air, they pretty much stay there for a long time, if not forever, because there are really no processes in the atmosphere that destroy them. But methane is different. Methane has a lifespan of only 1 decade, as you can see here. And that means it's not just produced, it's also destroyed. And that makes methane a very different gas compared to CO2 and nitrous oxide. And that is why methane has a different impact on climate. Not just are there differences across greenhouse gases, there are also differences between different sources of greenhouse gases. For example, these natural greenhouse gas sources such as swamps or cattle or rice paddies, they circle around the carbon in what's called the biogenic carbon cycle. Biogenic carbon cycle. So what is methane? Chemically, methane is CH4. Ever wondered where the C, the carbon from the methane, comes from? The C in the case of the biogenic carbon cycle, the carbon, originates in the atmosphere as atmospheric carbon dioxide. During photosynthesis, plants need carbon and they grab it from the atmosphere. In addition to that carbon, these plants also need sunlight and they need water. Again, that's the process of photosynthesis. That process is what the plants need to build carbon-containing molecules such as cellulose and starch. And these carbohydrates are the ones that livestock then eat to grow. So these carbohydrates, for example cellulose, are very abundant in the atmosphere. So what I saw when I flew over Ireland, all that green, that was by and large a bunch of cellulose. Grasses that when eaten are only really doing a service to ruminant livestock. Nobody else can digest cellulose but ruminants, such as cattle, sheep, and goats. Pigs can't, poultry can't, we can't. They can. They can take cellulose from marginal lands that cannot be tilled and cropped and so on. They take that cellulose and convert it. In fact, they're upcycling it. Not just are they recycling it, They are upcycling that non-human edible cellulose into beef, into lamb, into whatever livestock species that might be. So now I go back to the biogenic carbon cycle, but it's important for me to point this out, that ruminant livestock make use of cellulose by and large. So now that carbon is in the plant, and during photosynthesis, carbohydrates are produced in the plants. Sooner or later, ruminant comes along, let's say a cow, eats that plant material, and then a portion of that plant material and the carbon contained therein makes it into methane. The vast majority is converted into volatile fatty acids, but a relative small percentage is going into methane. Enteric methane is called, the methane that's belched out, and some more methane comes from the animal's manure. That methane, CH4, contains carbon, but that carbon that you see here is not new carbon, it's recycled carbon. It originated in the atmosphere in the form of CO2. That methane stays in the atmosphere for a decade, after which it's converted back into CO2. And the process by which that occurs is called hydroxyl oxidation. Nothing new. Chemists, physicists have known this forever. Why nobody ever put one and one together and explained that livestock methane is not new additional carbon to the atmosphere, but instead recycled carbon, is beyond me. It is beyond me, but it is such an important nuance in this discussion of the impact of livestock on climate that it is essential for you to know. So that CO2 that's resulting when methane is oxidized makes it back into the atmospheric pool of CO2, from which plants then suck again carbon out of the atmosphere and back into photosynthesis. So this is the biogenic carbon cycle. And in fact, it's a beautiful thing. It's solar powered, and it doesn't really require a lot of inputs. It needs the animals, it needs non-human animal feedstuffs, and it needs sunlight. So that's the biogenic carbon cycle, which must not be confused with other greenhouse gas producing processes, for example, those around fossil fuels. I'll talk about that in just a second. But what I want to point out on this slide here is that when you look at the beef herds and the dairy herds here in the United States over time, then you see some surprising developments. So you see on the top panel here that the beef herds increased between 1867 until the 1970s when they peaked. So the beef herds build up over time. They peaked in 1970. At the peak, it was 140 million beef cattle that we had in this country here. And since then, so since 1970 at 140 million beef cattle, we went down to now 90 million. So we are now having 50 million fewer beef cattle than we did in 1970. But with these 50 million fewer cattle, we are still producing the same amount of beef as we did in 1970. So that's quite interesting. Same trend on the dairy side, which you see in the bottom panel. Again, 1867 up until the 1950s. That's when we saw an increase in the dairy herd. In 1950, we had about 25 million dairy cows in the United States, 25 million. Since then, we went down to only 9 million today. So we went from 25 to now 9 million. But with the 9 million today, we are producing 60% more milk than we did in 1950, with a much larger herd. So that is really important to understand how efficiencies in livestock production and also better health and so on, better housing and husbandry conditions have increased milk production to such an extent where we have drastically shrunk livestock herds, both beef and dairy. Just as a little trivia, any idea how many horses we have in the United States? I just told you we have 9 million dairy cows. We have 9.5 million horses in this country. We have 170 million dogs and cats. Just to give you a little reference point as to what it means to have 9 million cows. So we've come a long way. By the way, when you look at this bottom panel here, you find something else interesting, I hope, which is that the last time we had 9 million dairy cows in this country here was in 1867. But at that time, we only had 30 million people. That was the population of the United States. 30 million people. Today we have 330 million people, so over 10 times as many, that receive all of their dairy products from a equal herd. Okay, so drastic improvements in livestock productions are the result of better genetics, better feeding, better health care, and so on. So I promised you to also talk briefly about fossil fuels. Oil, coal, gas are fossil fuels, and they are nothing but pure carbon that originally, a long time ago, were plants and animals. These plants and animals over hundreds of millions of years died, decayed, fossilized, and all that carbon material was then stored under great pressure in the ground. And you see it here on the left side underneath the ocean, on the right side on land. We have found ways to get to those fossil fuels and extract them. And within the last 70 years, we took out about half of all fossil fuel known to man. We have reached peak oil by now, and we have extracted that carbon from the ground. And what did we do with it? We burned it, meaning all that carbon from hundreds of millions of years of biomass was extracted within 60, 70 years, and we have put all that carbon into the atmosphere by burning it. And now every time the sun hits the earth, those carbon molecules heat up. And that, ladies and gentlemen, is the main reason. That is the 800-pound gorilla when it comes to climate. The unbelievable hunger and thirst for fossil fuels that we need in order to run our vehicles and power plants and airplanes and so on. That is the 800-pound gorilla. I will now show you a couple of slides that might sound quite technical to some, but they're very important to all of you. The first slide here shows the difference between a gas such as CO2 versus a gas such as methane. I told you before that the GWP100 simply converts everything to CO2 equivalents, right? To CO2 units. But that's not correct, it's not fair, and it needs to change, not just in my opinion, but in the opinion of many of my colleagues. What you see on this slide here is a development where we just simulate an activity of producing CO2 over 5 days. So let's just say, imagine you're driving to work. A non-COVID-19 world, you're going to work again, you're driving 10 miles in the morning to get to your workplace. So on Monday, day one, you put CO2 out when driving your car. On Tuesday, you make the same trip again. And now, as you can see, you add the similar amount as you did on Monday, also on Tuesday, but it's now on top of what you had already put out on Monday. On Wednesday, you add an additional equivalent amount of carbon to what you put out earlier that week, and so on. So what you can see here very clearly is that CO2 over time accumulates, it grows, and every time you emit CO2, you add new additional gas to the existing stock. That's why it's called a stock gas. It accumulates. It's not destroyed like methane is. Let's contrast that now with methane. Methane is not a stock gas. Methane is a flow gas. When you look at methane, when you put out methane from a constant source, let's say a constant herd, let's just say you were a beef farmer or a dairy farmer and you were to have a herd of 100 cattle. And let's say you started that business 50 years ago. Then only during the first 10 years of your farm's existence did you add new additional carbon to the atmosphere. Carbon that wasn't there before was now belched out by your cattle and emanated from their manure. But after the first 10 years, that constant herd of yours still produced methane, but at that time the amount of methane produced and the amount of methane destroyed balanced each other out. And that's what I showed to you in the biogenic carbon cycle. As long as you have a constant source of methane, the amount of methane produced and the amount of methane destroyed balance each other out. In other words, with a flow gas, unless you increase the source, let's say add additional cattle, new additional cattle, unless you do that, you are not adding new additional carbon to the atmosphere, and that means you're not adding new additional warming, but you are plateauing the amount of contributions you have. That's why it's called a flow gas, okay? So why am I showing you this? I'm showing you this because most people up until now simply act as if methane were to accumulate the same way as CO2 does. They treat methane as a stock gas, not acknowledging that methane is not just produced, but also destroyed. And that makes livestock look as bad as most of those articles that you read day in, day out. So please remember, methane is a very different type of gas compared to CO2. It's not a stock gas, it's a flow gas. If you want to know more about that, colleagues of mine from Oxford University published pretty extensively on this. Some of those articles are more in the non-technical literature, such as two of the papers shown here on the left and in the center, and some of them are in the very technical scientific literature in journals such as Nature, Science, and so forth. The group of Miles Allen from Oxford University is one of the main contributors to this line of research. They are suggesting, and pretty strongly so, to not use GWP 100 for short-lived climate pollutants such as methane in the future, but instead use a unit that actually predicts the warming of methane over time. Because that's what we're all about. Knowing what the activities that we do day in, day out, what they do to actual warming. Because remember, we want to reduce global warming by 1.5 degrees by 2050. That's the Paris Climate Accord. We want to reduce warming. So warming is what we need to know, what we need information on, and not simply some CO2e unit. I will now show you 3 scenarios here, and it's important to really let that sink in. 3 scenarios. The first one is an increase of methane over a period of 30 years, an increase of methane by 35%. So that's pretty steep. Let's say in your country you were to have, I just give you a number, 10 million beef cattle, and you were to increase that to 15 million beef cattle over 30 years. Then that would mean you increase the amount of methane put out by your beef cattle, right? Because you went from 10 million to 15 million. The second scenario is a slight reduction of methane, and that can be achieved by either feeding feed additives or doing something with the animal's manure, or maybe a slight reduction of animal numbers. That's possible and happening in some regions in the world. So a slight reduction of methane by, let's say, 10% over 30 years is the second scenario. And the third scenario is a decreasing scenario of methane, where you reduce methane over 30 years by 35%. So now let's see what the GWP 100 unit, what that would predict as a result of these 3 methane scenarios. GWP 100 would predict an increase of CO2e units, regardless of whether you are strongly increasing methane, whether you keep it stable, or whether you're decreasing it. And that again exemplifies why GWP, or how GWP, treats methane as a stock gas, acting as if it always were to accumulate, regardless of how much you emit, which is not true. It's physically incorrect. Now look at what this unit GWP star that my colleagues from Oxford are proposing makes a difference to that, and how it predicts accurately what these different methane scenarios would do. So here's GWP star. It predicts that if you increase methane by 35% over 30 years, that you see a strong increase in warming. No question, methane is a potent greenhouse gas. We do not want to increase it. And if we do, then that has a big warming impact. But what GWP star predicts is similar when it comes to warming compared to what GWP 100 predicts. Look at the second scenario. A slight reduction of methane actually leads to what's called negative warming. You see here that blue line south of the x-axis indicates that there is no additional warming at all. In fact, there is slight negative warming, which is another word for cooling. But what really gets me excited is the third scenario. What happens if you decrease methane by 35% over 10 years? If you do so, you will have a strong cooling effect. And that's what you see represented in this blue area south of the x-axis, a strong cooling effect. So of course people ask me, and they ask me all the time, is that even possible? Is that even in the realm of possibility that we can achieve a reduction of methane from livestock? And the answer to that will be given to you in a few minutes. Before I go there, a little bit more of theory around that, because it's that important. This slide here will show you three panels. The top part of each panel shows CO2 and methane emissions. So that could be from a power plant or from a cattle herd. The power plant, let's say, puts out increasing emissions of CO2 when you ramp that thing up. The cattle herd could increase emissions if you increase numbers, let's say, of cattle, for example. And then at the bottom you see what these increases of CO2 and of methane would do to warming. Namely, the increased CO2 emissions would lead to a exponential growth in warming. Look what methane does. If you increase methane, then you have a linear increase of the related warming. Okay, so that's the rising emission scenario, from concentration on top to warming at the bottom. This scenario here, the second one, shows, the center panel here shows a constant scenario of CO2 and methane. So what you see there is that if you keep CO2 constant, you see at the bottom that the related warming still goes up, and that's because CO2 is a stock gas, it's cumulative, it accumulates. Even constant CO2 emissions lead to increasing warming. That's why that gas is so troublesome. Look at what methane does. If you have constant methane sources, then that means you have constant warming, no additional warming. So a constant cattle herd, for example, putting out constant methane over time, over let's say 30 years or so, will not add to additional warming. That's what that panel shows. But now look at the third one, the decreasing emissions of both CO2 and methane. What do they do to warming? First of all, the decreasing CO2 still leads to an increase in warming, up until a certain point at which CO2, even increasing CO2, would plateau. But look at what methane does. You decrease methane, this short-lived climate pollutant, this flow gas, and you have an instantaneous effect on cooling. An instantaneous effect on cooling. So the climate responds to methane in a very quick way. Increases and decreases are reflected in changes of temperature instantaneously. And that gives us a real great opportunity to make impacts with our livestock herds on temperatures. Again, you'll ask me, is that possible? Let's take a look. So here at UC Davis, my lab does a lot of research on quantifying emissions of livestock, enteric emissions, manure emissions, silage emissions, and so on, and finding ways to reducing these emissions. So here you see the so-called bovine bubbles, in which I house cattle and find ways to reduce emissions. You see a wind tunnel that we use, for example, on commercial dairies to measure emissions from waste storage. You see a head chamber here where a cow sticks its head in, and we measure the belched out emissions of those animals and so forth. We do a lot of work for the state of California, and what shall I tell you? the state actually had very aggressive emission reduction goals of 40%. Many people wondered, can they be achieved? And the answer to that question is not just can they be achieved, they already have been achieved. The state wanted to reduce methane by 40%, 40, to be reached by the year 2030. And now, still 10 years away from that time goal of 2030, we have already reduced methane by 25%. So we are over halfway to reaching our emission goal of a 40% reduction. So again, we have reached 25 of that 40%. So over halfway there. And that amounts to 2.2 million metric tons a year. And as I said, makes up a total of 25%. So now think back to what that means to reduce methane, what that does to climate. It has a cooling effect, meaning the dairy industry that has achieved a 25% reduction of methane has actively pulled carbon out of the atmosphere. And by doing so, it had a cooling impact on the climate. That doesn't mean that our dairies are already off the hook or that they're already climate neutral or so, but they are on the path to being there because these reductions of methane will counteract other greenhouse gases such as nitrous oxide or CO2. We are not far from reaching climate neutrality of our dairy sector. And the more I look into this, the more I'm convinced that we can reach it for the beef sector, not just for the dairy sector, and not just in California, but in other states as well, and indeed in other countries. What's really critical is that we've got to get this methane scenario right. We have to understand how methane affects climate, and we now do understand that. And we have to understand how much our sector emits. Here in the United States, we have quantified that for beef, for dairy, for poultry, for pigs, and so on. I think they have to do the same. You have to do the same thing, so that you know what the impact is your industry has on emissions, on the overall emission inventory. And what's here particularly important is that you understand not just how important you are as a source of emissions, but also how important you are as a sink of emissions, because your land will have a significant sequestration potential that in Ireland is currently not accounted for. So when you think back to this little icebreaker slide I showed you at the beginning, all the carbon you are assimilating and sequestering that you're taking out is currently not counted toward the overall inventory. But only the emissions are counted, and they're all converted using GWP 100 into CO2 equivalent units, and not into an actual unit that predicts warming. So I hope that some of that or most of that made sense, and that you learned something here about methane in particular, and why knowing more about methane can really be instrumental for your farmers in reaching goals, and not just be viewed as a villain, as a problem that we need to reduce through lower consumption, but that you understand and that your stakeholders understand that agriculture can play a very important solution role, okay? It can play the role of a entity, of a sector that actually pulls carbon out of the atmosphere. And agriculture and forestry are the only two sectors that can do that. So whether it's our national governments or the IPCC, the Intergovernmental Panel for Climate Change, they all know that there are only two sectors that have the ability to pull carbon out of the atmosphere and store it in the ground. And you and I work with one of these sectors. So let's help them be successful. Let's help them to be part of a solution. And good luck with that. Please know that I'm not just here to do research and publish my data and communicate those orally like now, but we are also on social media. You will see here a slide showing the handle, the Twitter handle, both my Twitter handle and also the Twitter handle of the center, the so-called CLEAR Center here at UC Davis, a center that I'm very proud of. I'm the director of it. We are doing a lot of good work in this field of communicating the impact livestock has on climate, on air quality, on water quality, on and so on welfare and other sustainability issues. And we are communicating it quite aggressively. And with aggressively, I mean something good here. I mean, we're trying to get the word out of what the impacts of livestock are, and how we can further optimize them. So if you want to be part of that, be my guest. Thank you very much for listening, and all the best to you.
Thank you very much, Frank. And I hope that more work can be done in the coming years to tease out the evidence of the difference between emissions from ruminant animals and those from other sources, and indeed to have this reflected in the calculations of GWP 100. Our next speaker is Alec Higgins, who's a senior scientist at AFBI and who has been involved in soil and catchment modelling research to better understand how the application of slurry, manure, chemical fertilisers impacts soil nutrients. And once we've heard from Alec, we'll see a video from Ian McClellan's farm at Creevy House in Loch Brickland and the benefits that he has seen from taking part in this research.
Hello, my name is Alec Higgins. I work for AFBI, and I'm going to talk about some work that AFBI carried out as part of the EAA soil sampling and analysis scheme in the Upper Bann. Just as an overview of the webinar, I'm just going to take a bit of time to look at the scheme itself, some of the detail of it, and then look at the headline results and how we modelled the nutrient loss processes in the catchment, and look at some of the results of that, and then what conclusions we drew from this work. The EAA scheme was aimed to provide eligible livestock farmers with detailed information on their soils so that they could apply nutrients and lime in accordance with actual crop requirements, with a view to improving total farm profitability through increased grass and forage yields, optimized soil fertility, and optimized distribution of manure nutrients. And ultimately to improve the environment through a reduction of the risk of nutrient loss to water bodies, which is a big concern. And overall, a view of this is to improve sustainability at farm, field, and catchment scales. These objectives were going to be addressed by providing free whole farm soil sampling for participating farmers. The analysis results provided would be provided through an accredited laboratory, results tailored specifically to Northern Ireland requirements, which would allow the results to be used by the farmers for other purposes, such as in relation to the nitrates regulations. Free training was provided by CAFRI on soil report interpretation and nutrient management, which had been previously flagged by farmers as an issue. And as part of that, we developed these RAG maps, the red, amber, green nutrient maps for individual farmers. Red is indicating fields oversupplied with a particular nutrient. Amber is undersupplied with that nutrient, and green, those fields are at optimum levels. And finally, one of the objectives was to provide LiDAR mapping of the catchment to produce nutrient loss risk maps. And we'll take a bit more look at that later in the webinar. The scheme itself had two components, with approximately 20,000 fields being involved. The open scheme was available to all farmers within all livestock farmers, I should say, within Northern Ireland to apply for. 3,000 did. These were randomly selected down to 522 who ultimately participated. And as you can see, the wide distribution across the province. The second part of the scheme was the catchment scheme, and this was focused on the 11 sub-catchments of the Upper Bann, from Banbridge here in the north to Hilltown here in the south. 513 farms participated with a total of 7,300 fields. The distribution is a bit different from that of the open scheme, largely because of the actively recruited farmers from the catchment. So it's probably more representative of the distribution of enterprises, more representative of what's actually within the catchment. Okay, just in terms of headline results from the scheme, pH is probably the most important soil parameter, and the analysis would indicate that 40% of the area tested was found to require lime, and thus potentially losing significant dry matter production. And just to note that this 40% excludes those extensive areas of moorland and hill land. And if we look at in terms of the distribution among the enterprises, it's relatively evenly distributed with just a slight lowering with the more intensively managed dairy sector. Potassium, soil potassium is another key element for sustained production of grass, and the target index of 2-, and we found that 42% of the tested area of the grassland area fell below index 2-. And when we look at the distribution among the enterprises, it's not surprising to find that the sheep sector, which would be relatively less intensive than the others, has got a high proportion of fields below this. But dairy at 43%, or nearly 44%, is also surprisingly high. So there's, again, significant potential loss of production associated with that figure of 42%. Looking at soil phosphorus excess is the issue here. And if we look at the distribution of 38% in total of the grassland area within the catchment was found to be above index 2. And again, no surprise when you look at the distribution among the enterprises. Sheep, as the least intensive, has got a fairly small proportion of the area, oversupplied, but the more intensive sectors, particularly dairy, have significant area of their holding with excess soil P. Now, crop excess soil P is an issue because P is a growth limiting nutrient in aquatic systems. And any additional dissolved P in water can lead to increased algal growth or increased unwanted aquatic plant growth and significant reduction in water quality. Soils found to be at or above Olsen index 3 have been shown to lose higher rates of P, primarily through surface processes like loss of dissolved P or erosion of particulate P through either organic or mineral material being lost. The distribution of excess soil P is spatially uneven throughout the catchment. As you can see, the upland areas have no particular issue, that's the sheep-dominated areas, but the lowland, more intensive sectors have a significant P excess problem. And to focus on the potential management of this issue, LiDAR imagery was obtained for the catchment. LiDAR is an acronym, it just means light detection and ranging, and essentially it is a laser. It's a plane mounted laser which captures a huge amount of data. There'll be tens of millions of points across the catchment. It's got detailed height information associated with each one of those points. as this was flown in the autumn and winter with few leaves in the trees, it means that we were able to obtain information on the ground surface. So we could strip away the vegetation, and this is part of the processing of this. It strips away the vegetation, and you're looking at the bare surface of the soil. And this allows you the production of a water flow model for the catchment. And when we integrate this with soil data, looking at the infiltration capacities and the hydraulic conductivity and so on of the soils, you can generate these flow accumulation paths of the as water moves over the soil. And we're just going to make out these red areas here, which are these hydrologically sensitive areas where water will accumulate on the surface. And I think we've probably familiar with that. You're driving around at this time of year, you will see areas like this within fields which are prone to waterlogging after rain events. And essentially, these are zones of prolonged saturation and ephemeral surface water accumulation. And these represent the primary route for surface delivery of dissolved and suspended nutrients to the aquatic system. Now, once we have identified these areas, it allows us to produce the nutrient loss risk maps. And this is an example of the type of thing that would have been sent out to the farmers involved in the scheme. And each of their fields will be identified, the risk areas, and it will also, these purple dots, also identify the delivery points to the aquatic system. And the identification of these would potentially allow mitigation issues or mitigation strategies to be taken, like placing sediment traps or buffer zones, something to stop or slow down the delivery of the pea to the river. And the benefit of that is that if undertaken, it could potentially avoid blanket measures like the banning of fertilizer or organic manures on some of these high-risk zones. Okay, we just look at the water quality element of this. Part of the reason AFBI were very interested to be involved in this work is because AFBI have a long-established water chemistry sampling network within the upper band subcatchments. And this would allow us to look at the relationship of the water quality and these intensive soil measurements that we have through the scheme. These these catchments are sampled on fortnightly intervals. We have 13 subcatchments. 11 of those catchments were involved in the scheme, and two just outside the scheme. And as I say, it allows us to examine the relationship between the in-stream phosphorus, which is known as soluble reactive phosphorus, and this is the measurement that the Water Framework Directive uses to categorize good, moderate, and poor quality river waters. And if you look here, you can see there is a big spread in terms of SRP values within the 11 subcatchments. These two upland catchments are in the good to very good category, but as you can see, there's progressively, you moved progressively down the moderate scale for some of the other subcatchments, with a range from 8.5 to 145 micrograms. And this dotted line here is at 48 micrograms, and this represents the difference between good and moderate water quality in terms of P within the Water Framework Directive. And there's strong seasonal, very, very strong seasonal variation in this value as well. It's just a quick look at some of the actual measured data that was collected. The blue line is the actual volume of water being discharged, and the pink square is the median SRP value as measured in the 11 subcatchments or 13 subcatchments. And as you can see, this is the spring to summer period. You get a gradual increase in the concentration of SRP, this dissolved phosphorus in the water, up to, as you can see, a maximum value of just about 250 micrograms, which is pretty poor water quality. And as this is a median value effective and an average, some of the values are exceptionally high, going up to 12 and 1300 micrograms, so exceptionally poor water quality. If we go back to look at our relationship, you can see it's a very strong relationship between SRP concentration, the dissolved P in water, and the proportion of the subcatchment above index 2. And if we look at this point, which is the division between moderate and good, you can see we've got a value of about 15%. That's the threshold to avoid eutrophication. That's the threshold where you go from good to moderate quality. So in essence, then that the catchment can't have more than 15% of the fields above index 2, otherwise it slips into this moderate category. And another way we looked at this data was to include the proportion of the hydrologically sensitive areas. So in essence, we're saying the proportion of soils which are above index 2 and which contain these areas. And when you look at the same, in this case, it's not a linear relationship, it's a power relationship. But when you look at the intersection of the good to moderate line at 48 micrograms, the proportion of the catchment is 1.5%. Now, when we take the usual experimental error into account, it actually means that you probably can't afford to have any hydrologically sensitive area in soils above index 3. Otherwise, you cannot move from a moderate water quality to good water quality. Okay, just in terms of general conclusions, it was a highly successful scheme with over 70% participation. And we'd just like to take this opportunity to thank again all the participating farmers for allowing AFBI to collect this highly useful data. Sustainable increase in quality and quantity of grass could be achieved through correction suboptimal soil pH, 40% of grassland tested, and soil K values, 42% of grassland tested. Soil P levels excessive to plant requirements are a concern because of their potential impact on aquatic systems. 38% of the grassland tested above Olsen index 2. Water sampling indicates a strong relationship to the proportion of the catchment with either excess soil P levels and HSA in combination with excess soil P in relation to overall river water quality. Soil nutrient and runoff risk mapping can be a potentially useful tool to target and manage nutrients at farm scale, both to protect the environment and conserve a valuable nutrient. And I'll just leave you with a nice shot over to the moorings. Thank you.
I'm Ian McClelland and welcome here to Creevy House Farm. It's a grassland dairy farm. We're working at producing as much milk from forage as we possibly can. We've just finished 4th cut silage at the minute, so that's a harvest over for this year, I hope. We've been farming here now for 3 generations. It's come from my mother's side, and they had cows here in the 60s and 70s, but sold out when my grandfather died.
and there was just beef on here from then on. We started dairying here in 2015, built the new parlour and this new shed, and we've been going on now, we're up to 90 cows. At the minute we're using sex semen as well to minimise on the Holstein bull calves, and it has worked well. See it as a great investment. It's costlier at the time to inseminate, but it's working well here. Calves are all reared and calved early, 22 to 24 months, to maximise on their potential. Cows come out of this pen and into the calving pen to give birth. Calves are reared then to about 8 to 10 weeks on milk, on whole milk from the milking herd, and then weaned. Here we're milking Holstein Friesians. They're quite a high output herd, and we're trying to maximise our use from forage on this farm. We're breeding for fats and proteins, also milk yield, but maximising on fats and proteins for the payments. We're averaging just over 10,000 litres here at the minute, with 3,500 or 3,600 coming from forage alone. We're pretty pleased at the minute. We'd like to increase our milk from forage figure. This last number of years we've got our figures up every year, so hopefully we'll get to the 4,000 figure, which we would like to get to. The project involved getting soil samples from all the ground that was in the Banbridge catchment area. The soil was all analysed, and there was actually a radar or a LiDAR picture of the ground taken with where the most likely runoffs from, which was a very interesting point for sowing fertiliser and keeping up your nutrient management. So they came out to the farms all along the catchment area and did the sampling themselves. So on my part, I didn't have to do a whole lot for it. I just got the information, which was more than welcome. The soil analysis then left us with the information going forward for pHs and P and Ks in the soil. So actually my land is good Ps and good enough Ks at the minute, and just needs upkept with lime as and when is needed. We have good storage on the farm, which means we're not rushing in the springtime to put out slurry just if we need to. So we're usually going in the middle of February when it's good and dry, and we get the contractor in to spread maybe 2,500 litres on with a dribble bar, which is very efficient, low ground damage, low wastage of slurry or any nutrient loss, and you're using as much nitrogen then as possible. My grass yield has increased year on year from I've been in the project. Also my milk from forage has increased by around 1,000 litres over the course of the 4 years. As with every efficiency, it has reduced my cost of production. It leaves me that I don't really have to spread any P or K as chemical fertiliser. I can use my slurry to the maximum, with the slurry then just spreading straight nitrogen. We've planted quite a few bits of hedges here and repaired a lot of hedges. There's been a lot of hedges have got overgrown in the past and have grew away. As people know, they grow away up and they get very open in space. So we have made the decision and took down hedges, and people say, oh, that's awful, you're cutting the hedges away down, but it's not. It's actually, you're cutting them down so they'll grow back up nice and thick. And we've left the ground now where the hedges are improving every year. We trim them back every 2 years just to keep them in check, but we try and get as thick a hedge as possible to leave room for wildlife. That'll leave us in future hopefully getting more carbon capture from the hedgerows and the trees in the farm. We have a lot of bird life on this farm. We have a lot of we have ravens, and there's quite a few buzzards about. And like every farm, lots of rabbits and a few foxes running about. So we're pretty well serviced with wildlife around here.
Thank you, Alec and Ian. Now, another area that has an impact on a farm's emissions is livestock feeding. And that's something that Dr. Conrad Ferris from AFBI has been working on in recent years. And once we've heard from Conrad, you'll see another video, this time from the Drew and Valerie McConnell's farm just outside Omagh. Don't forget, by the way, to continue to submit your questions in the chat window, and please do use your Instagram and Twitter to engage with the event online. Conrad.
Thanks, Mike, for that introduction, and can I just thank you for the invitation to come along and give this presentation this afternoon. The presentation is about improving farm profitability through efficient concentrate use. It's an extremely broad topic, so I'm just going to be touching on a number of issues here this afternoon. I'm going to just begin by looking at trends in concentrate use and milk yields in Northern Ireland. This is based on CAFRE benchmarking data, so performance is a little bit higher than the average farm. But as you can see, over the last 15 years, concentrate intakes per cow have increased quite dramatically by over half a tonne. And that's also reflected in a trend for milk yields to increase from just under 7,000 litres to almost 8,000 litres. So the increased concentrate intakes have been reflected in increased milk yields. However, if we look at some efficiency indicators here, milk from forage being the first one, we can see that milk from forage did fall very dramatically, especially from 2004 through to about 2013. It is stabilized and has actually started to increase a little bit, which is good news, but milk from forage is a good indicator of concentrate use efficiency. The other indicator I want to look at is the number of kilos of concentrate required to produce each litre of milk. And you can see that this figure has increased fairly steadily over the last 15 years, probably leveled out a little bit now. Unfortunately, higher figures here indicate poor efficiencies. In other words, more concentrates are required to produce each litre of milk. So these figures certainly do give some cause for concern in terms of concentrate use sustainability. I think this figure, which again is from benchmarking, the most recent benchmarking year, 1819, that I could get data for, and it clearly shows that there is a huge range of efficiencies in concentrate use on local dairy farms. This shows milk yield against concentrate fed, and you can see a huge range in milk yields and a huge range in concentrate intakes. However, what I would like to highlight here, if we just pick a milk yield, the milk yield within sort of around the 7,000 litre range, you can see that the quantity of concentrates required to produce this amount of milk varies from about 1.5 tonnes of concentrate up to almost 3.5 tonnes of concentrate. So I should say each dot here is a farm. So some farms are producing 7,000 litres at 1.5 tonnes of concentrate, others taking almost 3.5 tonnes. And similarly, if we look at this for 9,000 litres of milk, some farms can produce 9,000 litres from 2 tonnes of concentrates, 2.5 tonnes, others take 4.5 tonnes. So there's a huge range of efficiencies in concentrate use on farms in Northern Ireland. If we then look just to very briefly examine how does concentrate use impact on sustainability. And again, I could talk on this for a long time, but very briefly, and I'll come back to some of these later. If we just look firstly at water quality, concentrates represent one of the key inputs of phosphorus onto our farms in Northern Ireland. And if we're bringing excess concentrates onto the farm, we bring excess phosphorus on with a negative impact on water quality. Similarly, air quality, and just focusing here on sensitive habitats and the impact on ammonia, which is extremely topical at present. And again, concentrates represent a source of protein, a source of nitrogen coming onto farms. And if that's used inefficiently, again, nitrogen gets lost as ammonia and other routes and that kind of a negative environmental impact. Climate change is the other big environmental thing we need to consider, especially in relation to greenhouse gases. And for concentrates, this is a lot more complicated because as we feed more concentrates, certainly the amount of methane a cow produces normally increases. However, the amount of methane per litre of milk probably goes down. So that's why when we look at greenhouse gases, we need to look at the overall carbon footprint, not just one metric. But certainly it is a sustainability issue. Going to look now just touch on some of the broader issues, and firstly global sustainability and supply chains. We know that a lot of our concentrate feeds come from parts of the world where they may not be farmed in an environmentally sustainable manner, and they also have very long supply chains. So again, that creates sustainability issues. I would also probably suggest there's a bit of a moral dilemma about feeding concentrate components that actually are human feedstuffs, and that's something I'll touch on later on. And finally, and perhaps maybe from a farmer's point of view, the most important sustainability aspect is financial sustainability. Concentrates are much more expensive than forages, and much more expensive than grass silage, grazed grass. And really, if concentrates are used inefficiently, it kind of a severe negative impact on the overall economic performance of the farm. So how do we tackle concentrate sustainability issues? Well, I'm sort of suggesting three very simple high-level titles here. Firstly, feeding the correct amount of concentrates, or feeding concentrates correctly, then getting the chemical composition of concentrates correct, and finally using the correct ingredients. So I'll just say a little bit about each of these just over the next few minutes. If we look firstly at feeding the correct amount of concentrates, I actually have to start here not by talking about concentrates, but really by talking about forage, because probably forage quality is one of the biggest determinants on how efficiently concentrates are used on our farms. I'm just focusing here on grass silage. Obviously, I could speak about grazed grass as well. But if we look at grass silage quality on our local farms, unfortunately, over the last 20 years, there hasn't been a long-term increase in silage quality, especially in terms of digestibility or metabolizable energy. So no long-term improvement. And yet that's so disappointing, for we know that for every 1% increase in silage D value or silage digestibility, we can actually have a concentrate saving of about 0.47 kilograms of concentrate per day. In other words, we can get if we improve silage quality, we can get the same amount of milk by feeding less concentrates. How do we improve forage quality? Well, we had a survey of 180 dairy farmers, and some of the issues raised by farmers are here, weather being one of the biggest ones there right at the center. But there are lots of other factors influence silage quality, and many of these are things that farmers can manage, especially issues such as sward quality and actual harvest dates. So forage quality, absolutely key to improving concentrate use efficiently. Just also, how do we actually feed concentrates and what's the impact of that? We've done a bit of work of this at Hillsborough over recent years. This study, we compared concentrates being fed using a feed to yield approach or a complete diet approach. And as you can see here, the first graph shows concentrate dry matter intake. And with the feed to yield approach, you can see we had a higher peak concentrate intake compared to the complete diet. But milk yield wasn't actually different with the two different approaches. Actually peaked higher with the feed to yield, but overall milk production was very similar. So I think I would really conclude here that different feeding systems can be equally effective, but provided each are managed correctly. And with complete diet system, that certainly involves grouping cows according to milk yield. The other concluding point on this is I'd say that concentrate levels must reflect the cow potential and silage quality. Getting those two things correct is absolutely critical. This was another data set looking at feed to yield systems, and in general, most farms in Northern Ireland have now adopted some sort of degree of feed to yield in their concentrate feeding. This is from a very large research challenge fund, AgResearch co-funded project involving 30 farms. And this is just a very small subset of data from that project, which very clearly highlights that as we feed more concentrates within a feed yield system, milk yields increase in more or less a linear manner. And that's as expected. However, what farmers often don't realize is quite often this kind of negative impact on milk composition. And you can see here, looking just at milk fat content versus concentrates, the more concentrates that were offered, milk fat tended to fall off quite dramatically. Didn't happen on every farm. Some farms the impacts were much greater than in this. So that's something that's really important. And I think the key conclusion here is that within feed to yield systems, especially monitoring milk composition with high concentrate levels is extremely important. Just a very practical issue to highlight here. And again, this is from the on-farm study. And this was actually just on 17 of those farms. We actually looked at the efficiency or the accuracy of the concentrate feeders. And you can see these are bars above and below the zero line, which is actually 100% accuracy. And just 4 farms to highlight: farms number 1 and number 2, and farms 16 and 17. You can see in these farms, concentrates were either being overfed or underfed by an average of between 10 and 20% on these particular farms. So that is a huge impact on how accurately we feed concentrates and how sustainable concentrate feed use is. So the key message here is check feeders on a regular basis. Going to move on to say a little bit now about the secondary, and that's getting the chemical composition correct. And I'm just going to focus here on phosphorus in this slide. I think most of us are probably aware that phosphorus in our water remains a major problem in Northern Ireland, and unfortunately, again, an increasing problem. Historically, dairy cow diets concentrates contained excess phosphorus. Back in 2001, that figure was around 6.2 grams of phosphorus per kilogram. Our research at AFBI demonstrated that we could very substantially reduce that amount of phosphorus in the concentrates to about 3.8 grams per kilogram, and that represented a 38% reduction. And indeed, our feed industry under NIGDA have made huge progress here. They have substantially reduced the amount of phosphorus in their concentrates, but I suspect that for long-term sustainability, that figure is going to have to be reduced even further. Just another very practical issue here with regards to phosphorus. Farms that make use of concentrates with a high level of efficiency will have also a much lower surplus of phosphorus on those farms. This was a bit of modeling from the benchmarking data that I did a number of years ago for cows with a yield band of around 7,000 to 8,000 litres. And this was really showing that on the most efficient farms, the phosphorus surplus was around 6 to 7 kilograms per hectare per year, whereas on the least efficient farms in terms of concentrate use, that figure was around 16 to 17 kilograms of phosphorus per hectare per year. So getting concentrate levels right, using concentrates efficiently, really critical here in terms of phosphorus. Also, just in the same sort of aspect of composition of concentrates, going to just mention milk concentrate protein levels. And we know that excess protein in the diet increases the amount of nitrogen that's excreted in both urine and in feces. And of course, nitrogen lost in feces and urine tends to result in nitrogen being lost as ammonia. And you can see the baseline map here for ammonia emissions in Northern Ireland. And we really do have a major issue with ammonia in Northern Ireland. Also, nitrogen lost as nitrogen oxide, a very potent greenhouse gas. And also nitrogen gets into waters and causes, by leached into water and causes enrichment there. Just really, how do we tackle this? Well, dietary protein levels can be reduced, we know that, and we have just initiated a major new DERA and industry co-funded research project at Hillsborough. Probably the target here is to see if we could reduce dietary protein levels from around 17.5%, 18%, which happens on many farms, to about 15.5% in early lactation, and maybe even more than that in late lactation. So really just moving on to the final area that I wanted to say a little bit about, and that is using the correct ingredients. And we know that in Northern Ireland, we have a high reliance on imported ingredients, especially soybean meal. And it's certainly been in the news a lot recently, the environmental impact of growing soya in countries such as South America. There are also long supply chains associated with these feedstuffs that we have to import, and also carbon footprint issues. We asked the question, can locally grown protein crops replace part of this imported protein? And that's an area we've looked at in our research. And we've actually focused on field beans, a crop that can grow in Northern Ireland. And we've shown that we can actually feed up to 4 to 5 kilos of field beans and dairy cow diets with no loss in performance, and yet replace about half of the soybean meal and half of the rapeseed meal in those diets. So going forward, that's going to become an area I believe is much more important. Finally, just highlighting the whole issue of the use of human feedstuffs in dairy cow diets. And this is within the context of a world population which is predicted to reach between 9 and 10 billion by 2050. And certainly use of cereal grains and ruminant diets is something that's increasingly being questioned, probably from a moral standpoint. The challenge that really faces the industry going forward is to be able to make more use of byproduct feeds, either byproducts from industry processing, human food processing, and even new sources of feeds, such as algae, insect meal, and others are going to be developed as well. So that's really going to be a big sustainability challenge in the future. So really just a final slide, what does sustainable concentrate use look like? Well, I would suggest it is feeding the correct amount of concentrate of the correct composition, which has been produced from the correct ingredients in order to supply nutrients that cannot be met with high quality forage. Mr. Chairman, thank you very much.
Hi, I'm Drew McConnell, dairy farmer near Oma, so welcome to our farm. I'm the third generation to farm here. We're mostly a dairy farm with some beef and sheep as well, which my wife owns. We're milking 160 cows with 50 of the highest yielders milked through the robot and the rest of them milked through an ordinary conventional parlour. So two things we've focused on this farm is breeding high producing animals that are efficient, that will produce milk for a long number of years, but they also help our greenhouse gas emissions because for every animal on the farm they're turning out a higher number of litres.
Calves are the most important animal on the farm. Try to treat them as if it was a newborn baby. Comfort and welfare and health of those calves are very important. They determine what our future herd is going to be like and how they perform.
Our replacement rate on the farm has been below 20% for the past 5 years, some years down as low as 16. So that means that the number of replacements we're keeping on the farm are quite small as well, and again that adds to our carbon footprint. You know, it improves it all the time. Average yields, they vary from year to year, but mostly in the 9,500 to 10,000 litre range. Milk from forage, we struggle here at times because we're in the west and we get quite a high rainfall, anything between 50 and 60 inches every year. But we're getting about 2,500 to 3,000. We're targeting 3,000 litres, and in an exceptional year, if we get a really good dry year, we can hit 4,000. Anybody that knows dairy, and the modern Holstein cow has a tremendous will to give milk. Most farmers will know about the negative energy balance. When a cow calves down, gives too much milk, she can't eat enough to support the milk yield she's given, so there she starts milking off her back. And when she breaks down, mobilises the fat on her back to turn it into milk, well then that draws off her reserves. The whole idea of the trial was, can we do anything to reduce that negative energy balance? The trial was set up to try and not build the cows up as quick as normal after calving. To do that, the type of concentrate we had to feed on the farm, we had to reduce the protein element of that concentrate down to 15%, because otherwise it's the protein that drives the milk production, so the more protein you give her, the more milk she was going to give. Did yields collapse? No, they didn't collapse, but they didn't rise as quickly as we thought they would rise. But what we did find, because of this fairly high energy ration, the 15% protein didn't drive milk in the early stages, and the build-up was quite slow over 30 plus days, and the cow didn't break down her body reserves as quickly as she did. That led to improved body condition, improved fertility, cows went back and calved quicker. When we looked over the lactation, that cow maintained her lactation yield at a peak for much longer. So at the end of 305 days, there was virtually no difference between the cows on the fast build-up and the cows on the slower build-up. That has led to cost savings because protein is one of the most expensive parts of the ration, and the other aspect of it is, again, is the ammonia. The less protein you feed to the animals, the benefit there is to the environment because it's producing less ammonia. Over this past number of years, we've let our internal hedges grow out a bit. We would only trim them once every 3-4 years, sometimes even 5. And by doing that, you can look at our hedges here, there's a lot more leaf in them for the area of the hedge. That has a carbon sequestration property, is it taking more carbon in from the atmosphere. But they also do, by allowing them to grow up, they produce more berries. In the past, we've always selected grass varieties which are very high yielding, but cows weren't really performing on it. So we've selected now grass varieties which have higher energy levels, so that we want to try and ensure that every bite of forage an animal gets is of the highest possible quality we can make it. We'll still soil test every 2 to 3 years. And with soil testing, we only supply the nutrients the plant needs. Less nitrogen has been applied, and again, there's a cost saving with that, but there's also an environmental saving as well. We lime as required, depending on the results of soil testing. Every time we reseed a field, which we do on average about every 7-8 years, we will lime at that stage, but if a soil test shows in between times that it needs lime, we will do that. We use a dribble bar to put on the slurry, and again, that saves fertiliser, saves nitrogen. Also, the other thing about the dribble bar, there's less ammonia released into the atmosphere. I've got to an age now where I'm getting to an old grey-haired farmer, and I want to leave everything in as good a state as I can for the next generation.
Thank you, Conrad, Drew and Valerie. Our next speaker is Martin Mulholland, a senior dairy technologist with CAFRE. Martin is going to share with us some insights from the sustainable young stock protocols in place at the CAFRE dairying unit in Greenmount. And after that, we'll hear from James Brown of Seaview Farm in Ballywalter, who took part in a research program looking at sustainable young stock management. Martin.
Good afternoon, ladies and gentlemen. Firstly, I would like to thank the organisers for inviting me to speak at this virtual symposium. The title of my presentation this afternoon is Sustainable Dairy Young Stock Rearing Protocols at CAFRE. My presentation this afternoon will cover why we are aiming to calve heifers at 24 months of age, recent CAFRE performance against this key target, accelerated growth in young calves, management of the newborn calf at CAFRE, the disease prevention protocols employed at the college, the use of automatic calf feeders, our grazing and housing management practices, and the use of genomic testing and sex semen to increase the rate of genetic progress towards a more sustainable dairy herd. As I go through the presentation, I will draw out the positive impacts of our protocols on sustainability measures and summarise at the end the impact of our protocols on the various aspects of sustainability, from economic to environment and social sustainability. Developing sustainable dairy young stock rearing protocols is work that CAFRE have been doing as part of the Interreg funded Dairy for Future project, which you can find out more about on the project website and on the CAFRE website. So why calve heifers at 24 months of age? Well, as you can see from the table, earlier calving results in fewer of the older and therefore larger non-milk producing replacement heifers on the farm. In the example of a 100 cow dairy farm with a replacement rate of 35%, this farm will have 30 fewer heifers over 24 months of age if calving heifers at 24 months compared to calving at 36 months. The result of this will be fewer animals emitting enteric methane, less land will be required, fewer heifer housing places will also be required. As a result of this, costs will be reduced, as will the workload, with fewer animals to measure. In work done a number of years ago, the cost saving of calving heifers at 24 months of age compared to 36 months was estimated at over £11,000 for a 100 cow dairy herd. Estimates by AFBI of the benefits of reducing the first calving age from a recently reported figure of 27.5 months down to calving at 24 months of age has been put at a reduction of 7% in the overall dairy farm carbon footprint. Turning to how we are doing at calfrey, as you can see in the table, in the last 5 years, heifer cows are generally being born earlier and calving earlier in the season, and that our average age at first calving is on target in most years to calve at 24 months of age. The earlier average date of birth has the further impact at calfrey of reducing concentrate fed to calves in the first summer, which I will touch on later in the presentation. As you can see from the most recent year, we have increased our age at calving by 1 month to 25 months of age. This is down to a deliberate movement in the start of our breeding season to allow us to start calving later, and as a result make better use of autumn grass on the college farm. In terms of assessing age at first calving on Northern Ireland dairy farms, on a number of occasions in recent years this has been estimated. The data would suggest that dairy farmers are making progress towards calving heifers at younger ages. In 2006, the estimated age was 32 months from analysis of APHIS data from farmers completing a detailed heifer rearing survey. And in 2016, the average age at first calving of heifers on Calfrey Business Development Group dairy farms was found to be 27.5 months. Further work is necessary to assess whether this improvement is continuing into more recent years. Turning to feeding of calves on the Calfrey dairy unit, we are trying to take advantage of the benefits of accelerated growth in our milk replacer feeding protocols, with milk replacer levels fed at up to 9 litres per day or 1.35 kilograms of milk powder, with the aim of achieving accelerated growth to rates of over 1 kilo of daily live weight gain during the milk feeding period. Research findings from a review of 13 published worldwide studies indicate that accelerated growth in the early stages of a heifer's life will deliver increased first lactation and lifetime performance, earlier puberty and breeding, and the research also gives indications of improved lifetime health and fertility. In our first winter in the new Calfrey calf house, we did not quite get these levels of daily live weight gain, in part due to not getting calves onto the automatic milk feeder early enough, which is something we have addressed for this new calving season. Turning to management of the newborn calf at Calfrey, hygiene management is critical to control the spread of diseases such as Johne's, as the calf at this stage is particularly prone to infection through feces contamination from Johne's shedding cows. Early feeding of colostrum at 10% of body weight after milking the cow with a portable milking machine in the calving pen is the standard practice at Calfrey. Surplus colostrum and transition milk from the first milking in the milking parlour is either pasteurised or acidified and refrigerated in the calf house for feeding during the first 5 days before the calf is transitioned on to milk replacer and moved into the group igloo pens, which are each equipped with an automatic milk and concentrate feeder at 7 days of age. As you can see from the image on the screen, the new Caffrey Calf House, commissioned in September 2019, incorporates an open plan canopy structure to maximise fresh air flow through the building. There is space for 40 individual calf pens mounted on wheels, which allow easy removal of the used pens to the wash bay for cleaning after each baby calf has been in the pen for 7 days. The building includes 6 igloos and associated bedded pens in front, which give the calf a choice of which environment to be in between the igloo and the bedded pen, depending on the weather conditions. To demonstrate labour efficient calf rearing to Caffrey students, 2 automatic feeders, each servicing 3 milk feeding and 3 concentrate feeding boxes, have been installed. Each milk feeding box is equipped with half body weigh scales to allow the performance of the calves to be monitored on an ongoing basis. Disease prevention, as I've mentioned, is critical to the effective rearing of calves on dairy farms, both at the Caffrey Dairy Unit and on commercial farms. The new building has been deliberately located on the edge of the farm facing into the prevailing wind, not closest to the dairy unit, and this is to ensure that clean, fresh air is blown in general over the calf house, as opposed to the wind blowing pathogens into the calf house from older stock housed in other buildings. We have strict pneumonia vaccination protocols in place, isolation facilities for sick calves.
I'm listening.
Such as industrial dishwashers and washing machines in the milk preparation room for cleaning milk bottles and calf jackets, respectively. The automatic milk feeders also come equipped with automatic teat cleaning equipment installed to minimise the risk of disease transmission via the milk teat. And we have staff and student hand and boot cleaning facilities at the calf house to allow students and calves to protect both themselves and the calves from disease infection. In terms of the automatic calf feeders that are installed in the new calf house, as I've said, these are equipped with half-body weigh scales. The data from the weigh scales is combined with the milk and concentrate intake for each individual calf in the Foster Technic Calf Cloud software to give a very clear indication of how each calf is performing. And you can see a page from the website software on the slide. This data is freely available to farmers purchasing new Foster Technic calf feeders over the past 3 to 4 years. The time available for this presentation does not allow me to go into any more detail on the new Caffrey Calf House. However, Caffrey will be hosting a series of 3 webinars on the new calf rearing facilities starting next month. During these webinars, we will go into much more detail on the design of the calf house and the calf management protocols employed. Turning to grazing and housing management practices at Caffrey, the calves are turned out to grass in April each year when grazing and weather conditions are suitable. Grazing results in lower ammonia emissions per animal than housing, so we aim to graze for as long a season as possible. A leader-follower system is practiced with the calves grazing ahead of the in-calf heifers. A comprehensive parasite and fly control system is practiced. September to November born calves get no concentrate at grass. If we have December or January born calves, they're grazed separately and fed 2 kilos of concentrates during the grazing season with the aim of getting them to target service weights earlier so that we can get them in calf at a younger age to calve down as early as possible in the calving season. During the second winter, the calves are housed in a purpose-built calf or heifer house, which incorporates ammonia emission reduction flooring to reduce the emission of ammonia from the building. In their second summer at grazing, The heifers again receive no concentrates and are followers in the leader-follower system. Turning to breeding and the use of genomic testing. All female dairy cattle on the Caffrey dairy farm are genomically tested. As indicated in the table, the key breeding indices associated with dairy farming sustainability are being improved within the Caffrey dairy herd, including the overall PLI index, as you can see, has increased over the last 8 years from 20 up to 221. Fertility index is also improving, as is lifespan, and somatic cell count is getting more negative, which is what we are looking for in terms of that particular measure of genetic merit. At Caffrey, the individual genomic merit data is used to decide which females to breed replacements from, and if there is a surplus, which heifers to keep and which to sell. On commercial dairy farmers breeding potential dairy sires, genomic analysis is also a highly effective tool to select potential sires for breeding. At the college, we use sex semen combined with the genomic testing results to breed most of our replacement heifers from maiden heifers, with the aim of increasing the number of milking animals in the herd that we can breed to beef sires, to optimize the value of crossbred calves and to reduce the number of Holstein bull calves to very low numbers ideally. The sires chosen to breed replacement from are first selected from the top 25% of available sires by PLI. PLI, as I'm sure many of you know, is continually being updated with recent dairy sustainability related indexes added, including maintenance, to ensure that over time the size of cows reduces, and as a result this will reduce the maintenance energy requirements and hence enteric methane emissions, etc. Other indices added to the PLI include those for TB resistance, dairy carcass index, calf survival, and lameness resistance in recent years. Sires are also chosen from both the proven sire list and from the genomic young sire list. After first screening for PLI, secondary selection is then made based on fertility index, lifespan, milk protein percentage, etc. So to summarize, ladies and gentlemen, in this very short presentation, I've briefly described some aspects of sustainable dairy young stock rearing protocols at Caffrey. In the summary table displayed on the screen, I've attempted to indicate which aspects of the dairy farming sustainability matrix, from economic to environmental and social sustainability, our management protocols are impacting on. As you can see, we're employing measures to improve all aspects of sustainability, from economic, environment, and social. And in the case of social sustainability, I have divided those into consumer and antimicrobial resistance impacts. Going forward, there is work to do to tease out the individual and collective impacts of these measures on sustainability through ongoing DAERA commissioned research and new decision support tools which are under development by AFBI and Caffrey. Ladies and gentlemen, thank you very much indeed for your attention. And if you have any questions, I will try to answer them during the question and answer session at the end of the webinar. Thank you very much.
Hello, my name is James Brown, so welcome to Seaview Farm. The original farm was only 30 acres. On this block here we're standing on is now 46 hectares, which is about 115 acres. The herd is made up of about, I suppose, 75% Nibby Ayrshire. There's 15% Norwegian Red that are still here from a project that was many years ago at Ellsworth. We measure the grass there, and we're utilising 11 tonnes of dry matter per hectare. We're just using our own slurry. We're not buying in P phosphate as well, so the nutrients are really potash and nitrogen, two main plant foods that we use. All the slurry that goes on to the first and second cuts is done with a trailing shoe, mainly because a lot of the silage ground is heavier ground, and so we don't want any compaction at all, and also we get better use of the nutrients and there's less losses. Because I'm a dairy-gated farmer anyway, all the farmers soil test it once every 4 years. We know exactly where our fields are in terms of pH, and we're fortunate that pHs are quite high, but we will be putting lime on this year. At the minute the cows are mostly spring calving. There's 20% calve in the autumn and the other 80% calve in the spring. We make sure that we start calving about the 15th of October and don't stop for a break on the 8th of December, 10th of December, and then we start again the 10th of January, and the main block, most of them calve between then and the end of March. We're milking 160 and there's about another 100 followers. And somewhere over 3,000 litres from grass. We've just 9,000 litres per hectare from forage, average over the last number of years, about 1.2 tonnes of concentrates. It means that per million litres of milk that we sell, we're probably using 100 tonnes less concentrates than a high input system. So it means that phosphate balance here is considerably lower. Average 3.4 protein for the year and 4.3 butterfat. The Young Stock project from Hillsborough, the Research Institute, was really involved in monitoring the calves right through from birth right up to calving. And so we would weigh the calves at birth, and then they were weighed periodically during their up to the end of their first lactation. I needed to get the heifers a bit heavier at calving, and so that's what we'll focus on now. And we'll focus now on doing the calves better in their first 100 days. Then it's a lot easier right through their life. We're calving at 24 months, which has cut down our replacement rate. I'm getting quite a few lactations out of my cows. The replacement rate is really it's about 21% at the moment, which is just on the low side. We could do with bringing in some more replacements, but it does mean whenever we're calving at 2 years old, we'll have a batch less stock on the farm. Obviously that works well with emissions as well. If you have less stock, less emissions. Our management now starts really before the calf's born, and it's very important to get a lot of minerals into the dry cows, and that produces a hardier calf at birth and a more virile calf at birth, and that means that the calves then have a more immunity to scars and diseases. One way that I could do something for the environment was raise the level of the hedges, and the majority of them now are up in around 9 feet. And this is a level they used to be cut at. It's what is quite traditional in a lot of farms, hedges cut low. But I found it was quite severe on them, and I wanted to increase the size of my hedges to get more bird food really and more cover. And it's also good for sequestration Obviously, the more volume of the hedge, the more carbon it can sequester. And even in the summertime, there's a lot more cover there for birds nesting. It really is good, and you can see the hedge is nearly moving with birds at times, so it is a big benefit to us on the farm, I think. And also, especially in the two, I go out early in the spring with the cows, and it means that there's shelter for the cows there, and that's the important thing. We do get quite a lot of hares. There's a lot of hares on this farm. You can get up to 5 in the one field, which is quite uncommon. Whether the number of hares on the farm is to do with the height of the hedges or I don't know, but certainly there's a lot more cover for them now.
Thanks, Martin and James. The United Nations has identified 4 pillars of sustainable diet. It needs to be culturally acceptable, affordable, have a low environmental impact, and deliver good nutrition. Our final speaker this afternoon, Dr. Stefan Peters from the Dutch Dairy Association, has been involved in research to look at these 4 pillars from a dairy perspective, and in particular to assess the environmental impact of different dietary approaches. This work is ongoing, and I'm delighted to welcome back Stefan to give us an update on the role of dairy foods in a healthy, sustainable diet in Europe. And please do continue to submit your questions for the panel session that will follow Stefan's presentation.
Hello, my name is Stefan Peters. I am Manager Nutrition and Health at the Dutch Dairy Organization. And today I'm going to show you some results that we have obtained with making calculations with the linear programming model Optimeal. And before I show you the results, I will give you a short introduction of the background of the work that we have carried out. And therefore I have to share my screen. And well, what the basis is of our research is this eating wheel that we hear a lot. An eating wheel says eat a less animal and more plant-based diet. And with eating a less animal and more plant-based diet, it is assumed that the ecological footprint of a diet will decrease. Well, this is stated by, for example, Greenpeace, with their report Less is More, and where they advocate that in 2050, we should consume as a world population 50% less animal-based products and also produce 50% less animal-based products. And of course, you might have heard, I guess, of the Eat Lancet report, in which they also have calculated a diet in which they assume that it will decrease the ecological footprint of a diet, and also based on the assumption eat a less animal and more plant-based diet. Well, these assumptions are made based on so-called life cycle assessments. And in life cycle assessments, you can calculate the carbon footprint of per kilogram of products, whole range of products. And here I've got an example for you of different carbon footprints of different products. And indeed, if you compare the carbon footprint of different products per kilogram product, then you can see that the animal-based products on the left side of your screen do indeed have a larger carbon footprint than plant-based products. So, based on the carbon footprint per kilogram of products, you can assume that eating a less animal, more plant-based diet will indeed decrease the carbon footprint of your diet. However, it is not that simple, because animal-based products in our current diets provide for a considerable amount of minerals, vitamins, and proteins. For example, animal-based products, milk, for example, provides for more than half of the calcium in our diets. Meat, for example, provides for almost 90% of iron in our diet. And if you look at vitamins, then you can see that vitamin A is provided for by animal products almost by a half, and vitamin B12 for approximately 75%. And this is based on the Dutch Food Consumption Survey, so the average Dutch diet. That means if you would decrease or eliminate animal products from your diet, that of course you have to compensate for the nutrients that you are losing in your diet. And if you do not do that correctly, then it might have as a consequence that the nutrient intake will be far from optimal. Well, in the Netherlands, there have been made different calculations based on the average diet and see what the consequences on the ecological footprint can be of eliminating animal-based products. And in this figure, you will see an example. And I'm going to explain you what this figure is about. Let's first have a look at the black bars. What they did here is the following. They have calculated the carbon footprint of the Dutch diet, and then they replaced in the model all meat and dairy by meat alternatives and dairy alternatives that are marketed as so in the supermarkets. And when they replace 100% of meat and dairy, then indeed the carbon footprint of the diet can decrease by between 15 and 30%. However, the consequences of replacing meat and dairy by alternatives for the nutrient intake are shown in your screen now. And if you look at the black bars, these are the consequences of changing all meat and all dairy in the diet. And what you see is the following, that the saturated fatty acid intake and the fiber will decrease and the fiber intake will increase because you have to eat a lot of more vegetables and fruits. On the other hand, the protein part of your diet will decrease by more than 20%. Calcium intake will decrease. Zinc, vitamin A, vitamin B2 and B12 will decrease considerably. Iron intake will increase a bit, but this is non-heme iron, so this increase can be neglected. And vitamin D intake will increase also a bit, but you have to consider that the vitamin D intake by the diet is quite low on average. But these are the consequences in the black bars of changing meat and dairy in your diet by plant-based alternatives. And for public health, it might mean that we have to be very vigilant with what happens on the nutrient intake. And there are nutrients of concern, that is vitamin A, vitamin B12, vitamin B2 and calcium in different parts of the population. So we have made calculations now with Optimeal, and Optimeal does similar calculations as what you see in your screen now. But when we are decreasing, for example, meat and dairy in Optimeal, Optimeal will compensate for the nutrients by increasing the intake of other products and then compensate for all nutrients that I'm losing, and then it can calculate the CO2 footprint of the diet. I'm sorry. And this got different advantages because we can not only now consider both the health aspects and the environmental aspects of the diet, but in Optimeal we can also see what the prices in the supermarket basket of consumers. And Optimeal also takes care of the fact that the alternative diet will be as close as possible to the diet that I'm starting with, and that is the principle of linear programming. And I know that this is difficult to imagine. That's why we have developed this tool. And this tool shows the results that we have made with the calculations with Optimeal. And now to have a good idea of what linear programming is, it does the following. On the left side, you see grams. So this is grams of the products that we consume approximately on average in the Netherlands. We consume about 360 grams of dairy per day. We do not consume 270 grams of vegetables today, but in our model we had to take this. I will not explain that why, because we do not have enough time. But just to give you an idea of the principle behind linear programming, we can do the following. Take, for example, meat. If we would decrease meat intake in our diet, we will be losing proteins, we will be losing vitamin B12, we will be losing iron. So when I will decrease the meat intake of in my diet, Optimeal search for other products of approximately 210 products in total to compensate for the nutrients I'm losing. So we have to eat some more fish, beans and pulses to compensate for the protein I'm losing, some more nuts and seeds, etc. And this is the vegetarian diet, which can be consumed as alternative to the average Dutch diet, providing for exactly the same nutrients as the diet with meat. We can do exactly the same for example, decreasing dairy. If I will decrease dairy in my diet, Optimal will calculate an alternative diet which provides for exactly the same nutrients that I'm losing in my diet. And what you see, for example, is that my beans and pulse intake is increasing, compensating for proteins, and I have to eat a lot of vegetables, probably to compensate for the calcium I'm losing in my diet. And so this is how we can change product groups in the diet and calculate an alternative diet with exactly the same nutrients. So this is the principle of Optimal. And we have done this by steps of 20 gram per product and product group. This is the principle of linear programming. We did also do an additional thing. Because of all these 210 products, we also have the carbon footprint calculated. Now things become interesting because, for example, when I would decrease my meat intake, Optimal will calculate for an alternative diet that is as healthy when it comes to nutrients as my starting diet, and it will calculate the carbon footprint which you see on the right side of your screen. And indeed, if I would decrease my meat intake and compensate for it in a healthy way, so compensate for all nutrients I'm losing, the alternative realistic diet will indeed have a significant lower carbon footprint. If I will increase, for example, bread intake of whole grain intake, then I will be increasing my plant-based products in my diet, and indeed the carbon footprint will decrease. And if I will decrease my dairy intake, decreasing an animal product group, then you would expect that the carbon footprint will decrease of the alternative diet, but it does not. And why is that? It might surprise you, but on the other hand, you know that dairy is a very nutrient-rich product group. And if I'm decreasing dairy out of my diet, I have to compensate for a lot of nutrients. And for example, if I will decrease dairy intake to 0, I have to compensate for calcium intake with a lot of extra vegetables. I have to compensate for the proteins with more beans and pulses. And the sum of the CO2 footprints of all these alternative products, I have to compensate for the nutrients that I'm losing. That sum of the CO2 footprints is exactly as high as the sum of the CO2 footprints of my diet with dairy. So actually, when we dive into details, when it comes to eat a less animal and more plant-based diet, then you could indeed say, based on these calculations, that decreasing meat in your diet will decrease your carbon footprint, increasing whole grain products will decrease your carbon footprint, decreasing dairy intake will not lead into a lower carbon footprint. Vegetables and fruits, it lies a bit more complicated, because if you will increase your locally produced vegetable and fruits, then the carbon footprint goes down. But if you increase more exotic fruits and vegetables in your diet, then the carbon footprint goes up. And we've got another add-on, and that is the price of these diets. So we can also see what are the effects of changes in the diet for example, meat. If we decrease the meat intake into our diet, the carbon footprint goes down, and the alternative diet is about between 5 and 10% more expensive. If I'm increasing my bread intake, the alternative diet will have a lower carbon footprint and will be about 5% cheaper. On the other hand, if I'm decreasing my dairy intake, the carbon footprint, as I've explained to you, will not go down, but I have to eat a very different diet with a lot of fruits and vegetables, more beans and pulses, and the price of my diet will go up and up. That is mostly based on the fact that the vegetable intake will increase. That means that decreasing dairy in your diet will not lead to a lower carbon footprint, but if you want to compensate for dairy in a healthy way, the price of your grocery shoppings will increase by between 20 and 30%. So this is an overview of calculations that we have made. And if we go to general conclusions, then if you want to eat a sustainable and healthy diet, You should, of course, eat less calories if you can do so, because then the ecological footprint will go down. Eat less snacks, sweets, eat less red meat, eat more whole grain products, and then eat fruits and vegetables, of course, higher than on average in your country and according to the recommendation, and as local as possible. You should keep dairy intake at current level, because dairy is a nutrient-rich product and guarantees the intake of a lot of essential nutrients. Drink less soft drinks and alcoholic beverages. And so the paradigm, eat less animal and more plant-based diet, is actually a too general eating rule. There are a lot of more details behind it to do it, to decrease the ecological footprint of your diet in a healthy and sustainable way. Well, of course, you say, Stefan, you are the Dutch dairy industry, so obviously you would say this. However, these calculations that we have carried out have also been carried out by Wageningen University in the Netherlands and have been published in a peer-reviewed journal confirming our data. About 7-8 years ago, WWF did similar calculations for the UK situation, in which they calculated a diet in 2013 or 2012 and a new diet with a lower ecological footprint, which you should consume now, which you probably will not. And also here you say that is the orange pie piece, that dairy intake stays exactly the same, and you should eat less meat. And I've also mentioned earlier that the Eat Lancet Commission also made a healthy and sustainable diet. And also here you can see that on the right side of your screen, you see that they still provide with 250 grams of dairy products per day. So deleting dairy from your diet is actually too difficult to provide for an alternative healthy diet. And if you do so, the new healthy diet will not have a lower carbon footprint. Again, what is now a sustainable diet? A sustainable diet is not only a diet with a lower environmental footprint, but should also be very healthy and providing for all nutrients that we need. But this should also be acceptable for consumers. So if everybody goes to a vegetarian or vegan diet, I don't think that we will manage to get people there. And on the other hand, going to such diet can lead to very significant health and nutrient consequences. And of course, this alternative diet should be economically friendly, so consumers should be able to pay for this diet. And I hope that with our calculation, I gave you some insight in how you can eat a more healthy and a more sustainable diet. These are our conclusions, and these conclusions will also be provided for in a public website, which will be shared with you after this symposium, in which you can also do similar calculations that I did in my screen. So I want to thank you, and I'm very curious about your questions.
So I hope that you found today's event interesting and formative, and thank you for taking the time to join us.
Thanks, everybody. Goodbye.
Cheerio. Thanks, everyone.
Bye-bye.